is Nur Fatadiana binti Muhammad Khairul Anwar, matrix ID CD200 and 209. Right, we are from group 10. There are 5 members of it. The title of our group assignment is determine the characteristic of vibrating system in car suspension. Next one, I will like to present about an introduction. The introduction of this project is about numerical analysis or numerical method is an approach to solve a mathematical problem for which there is often no analytical solution by approximation. Right, because of it, mathematical problems in natural science and engineering are often too complicated and cannot be solved immediately. With the help of the software like MATLAB, FreeMat, and Maples, and etc., methods were developed, analyzed, and implemented to solve discrete mathematical numerical problems. Right, the numerical method is used in a variety of real-world applications, which can include problems in algebra, geometry, and calculus, natural science, social science, engineering, medicine, economics, and other fields will always involve some degree of mathematical problems. Fortunately, as technology advances, so does the power and accessibility of digital computing. After all, the diverse possibilities of using realistic mathematical models or algorithms in research and technology can constantly develop.
Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Irfan Hakim bin Fazailah. Today I'm going to present about eigenvalue and eigenvector in real-world problem. So for the first example is the bridge construction. As we know, natural frequency which are thought to represent bearing condition and define resonant events under periodic loads are commonly detected by acceleration measurement using bridge sensor. Eigenvalue can also be used to inspect a solid for fractures or defects. When eigenvalue are employed, the issue takes less time to solve. The inherent frequency, which is eigenvalue, of a beam can be heard when it's impacted. If the beam rings, it is not faulty. A faulty beam produces a dull sound because the eigenvalue shifts as a result of imperfection. Sensory machines can be utilized to be precisely see and hear eigenvalues. Next is the suspension of car. When identifying the characteristic of vibrating system in automotive suspension system, we frequently utilize suspension natural frequency as a starting point for determining wheel rates when designing a suspension for a car weight, aerodynamic, and also tires. It is crucial to monitor and understand the suspension natural frequency in order to guarantee that the automobile is properly constructed and that the suspension system lasts as long as possible. In this project, we use this topic with the suspension of car as our main. For the final example of the real world problem, we have the stability of control system. Eigenvalue can be used in this control system to determine whether a fixed point, which is also known as the equilibrium point, is stable or unstable. A stable fixed point is such that a system can be initially disturbed around its fixed point, yet eventually return to its original location and stay there. The eigenvalue of a system linearized around a fixed point can determine the stability behavior of a system around a fixed point. The particular stability behavior depends upon the existence of a real and imaginary component of the eigenvalues, along with the sign of the real component and the distinctness of their values.
So for the method of assessment, the real-world application that have been chosen in this project is the application of eigenvalue and eigenvector in determining the characteristic of vibration in car suspension system. So to properly design a suspension for a car weight, aerodynamic, and tires, the engineering often use suspension neutral frequency as a starting point for picking wheel rate. Therefore, it is important to measure the suspension neutral frequency to ensure the car is properly designed. In this project, we choose Dua MyV as our model to demonstrate the application and calculation involved in eigenvalue and eigenvector. So this is the free body diagram of our car suspension system, which we can assume that the system have two mass and two spring rate, which is the mass is mass of the car on each tire and the mass of the tire, while the spring rate is the car suspension spring rate and the tire spring rate. Before we proceed to the calculation, we need to identify first the value of the variable in the car suspension system. So from the data collected, this is the value of the variable which involved in the vibration on the suspension car. To begin for our calculation, so based on the free body diagram of the car suspension, we can generate the general formula from Hooke law, which is F equal to Kx. So for the F1, we get Ks Kx1 minus Ks x2, while for F2, we got Ks x1 minus Ks plus Kw x2. Next, we can also generate the general formula from Newton's second law, which is F equal to ma. For F1 is mc x1 double dot, while for F2 is mt x2 double dot. After that, we can combine both of the equation of motion and we can get mc x1 double dot minus ks x1 plus ks x2 equal to 0, and empty x2 double dot minus ks x1 plus ks plus kw x2 equal to 0. So for this equation, we can change this equation in terms of vibration system, which the general formula for the vibration system is shown in this slide. So this is the equation of motion in terms of vibration. After get the equation, we can simplify the equation above with divide by sine delta t for both sides. After that, we simplify again the equation with divide by mass for each equation for both sides also. After finish simplifying, we can change the equation that we get before in matrix form. So the matrix form we can get as shown in this slide. After that, we let omega square is equal to lambda, and then since velocity is not equal to 0, so the a minus lambda I equal to 0 is the characteristic equation, while lambda is the eigenvalue and v is the eigenvector of the system. So to get the natural frequency, we can use the characteristic equation, and then we put all the value of the variables into the matrix A, and then we get the new matrix A as shown in this slide. After that, by using Cramer's rule, we can get the quadratic equation of the matrix A is lambda 2 minus 7.14 lambda minus 0.193 equal to 0. And then by using calculator, we can get the eigenvalue 1 is negative 0.0269, while for the eigenvalue 2 is 0.1679. So that we recall back that lambda is equal to omega square, so we can get the angular natural frequency of the system. So for the first natural frequency is 0.1640 imaginary rad per second, while for the second angular natural frequency is 2.6773 rad per second. With that, we can also obtain the natural frequency of the system. So the first natural frequency is 0.026 Hertz, and the second natural frequency is 0.426 Hertz. After obtaining the natural frequency, we can calculate the eigenvector for each eigenvalue. So by normalizing V1 is equal to 1, we get the eigenvector 1, V2 is equal to negative 0.7255. While for eigenvalue 2, by normalizing V1 equal to 1, we get eigenvector 2 for V2 is 74.143.
Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Faiz Ahmad bin Abdul Manap, and today I will present about result and discussion. As for result, there are two answers that we obtain, which is from calculation and another one is from pre-math. As for calculation, eigenvalues that we got are negative 0.0269 and another one is 7.1679. As for pre-math, the answer that obtained from it is the same as the answer that we got from the calculation. And now, I will present about discussion. First, natural frequencies are unique to each system, and they reflect the properties of the system. While mode shapes are derived from the eigenvectors, the natural frequencies are derived from the eigenvalues. Next, the characteristic equation is the equation that embodies the characteristic. A minus lambda I equal to 0 is called characteristic equation, and lambda is eigenvalue, and V is an eigenvector. This system eigenvalues are negative 0.0269 and 7.1679. These systems' eigenvectors are 1, negative 0.7255, and 74.143. So, the natural frequencies of the system are 0.026 Hz and 0.426 Hz. By prior discussion, the value of natural angular frequencies are 0.1640 I and 2.6773, which is the first angular frequency is the imaginary number.
Assalamualaikum, my name is Najwa Nurul Muhammad, my matrix number CD 2051. I will continue my part where is conclusion and recommendation. As we know, numerical method can be used or can be applied in the real world problem to solve it. As we know, the characteristic of vibration system can be found in the construction, in the applications such as bridge constructions, car suspensions, and stability of control system. In this project, we use the eigenvalue in the eigenvector to solve the problems. The eigenvalue and the eigenvector can be find out the natural frequency and define the resonance even under the periodic. To find out the natural frequency also can be find or can get by manually or confirm it the value is true, is correct. we can use software such as MATLAB, FreeMat, or Maples, or other software that related to it. So what can I conclude that the both methods, which is used by using FreeMat and by calculation, we get same value for the natural frequency. What can I suggest and our group suggest that besides by using eigenvalue and eigenvectors methods to solve the application in the real world, we suggest to use interpolations such as Lagrange interpolation and spine interpolation to solve the problems in the real world problem.